Today we will discuss about configuration space for motion planning. So this concept of configuration space is very well studied in the domain of mathematics as well as physics, and we'll use some concept of topology as well. But in this introductory lecture, we will try to mostly keep it a bit maths free. That means we will mainly look at various definitions and example. And in subsequent lectures, we will dive into details of object representation in configuration space and how we do the actual motion planning. And in this lecture, we will mostly try to understand that how we formulate a motion planning problem in configuration space. So we will indeed require a bit of prerequisites. I think we already discussed about some of them, like set theory, set operations, you may remember from your high school days. And we will also use a convex sets, and where we will further elaborate on the concept as we go along. And also we'll discuss about complexity of algorithms. So we discuss about this time space complexity, big order notation, when we compared these state space search algorithms like DFS, BFS, Ester. And I think at this point, we are already well accustomed with the basic concepts of graph theory in terms of trees and graphs. And in this lecture, we'll start with the basic definitions and concepts. Then we look at the motion planning problem, which we already looked at during the previous lectures. But here we'll talk about that how we can extend the same problem in a higher dimensional space. We'll briefly talk about obstacles, and then we will talk about a few uh, way of solving this motion planning problem in configuration space. And you will see that whatever we have discussed previously in terms of discrete motion planning, some of these concepts are still valid here. And in the penultimate slide, we will look at this piano movers problem, which basically looks at an old problem, but that will also nicely formulate the whole motion planning problem, considering both the robot and the obstacles, which we will further elaborate in the next lecture when we discuss about the obstacle representation. And of course, we will talk about efficiency little bit. So these are the sources. So today's lecture mainly will be based on the same textbook by Russell and Norvig, this modern approach to artificial intelligence. And also I will use some concept from this Stephen Lovell's planning algorithm book. But I also used a few slides from these various sources. So you are most welcome to explore them. And some of them are really good if you wanted to go into further details or want to understand the concept in more details. So first we look at the basic concept. So this is one example that we took from the value iteration class, that where we have this fixed base bot, and we were trying to move this bot without touching this hand. And we use this Google Media Pipe to detect hand. And then we discretize the whole space where the robot end effector can move. And we put some higher values on the terminal state, which designate this target. And we also put some negative values where the hand is there, because I do not want the robot end effector to touch my hand. And we show defined motion planning where we increase the uncertainty or probability of uncertainty in the robot's movement. So here you can see that we discretize the physical space where the robot end effector can move, and it has the advantage that we can really visualize it. That whatever we are discussing in terms of abstract maths concept, but we can visualize it. The mapping is also pretty easy. That we just map it from the video frame to the robot workspace. And it's a two-dimensional space. We can easily also extrapolate it to a three-dimensional place. But one big problem in this approach is that we are completely missing the orientation of the end effector. And this was a very simple exercise just to reaching task, that bringing the end effector to a position. But in many practical applications, we have to also deal with the orientation of the robot. And as we discussed in previous session that when we get a robot or buy a robot, we can directly program or send instruction to its joints, and we can send current to the say, servo motors which are controlling this joint. And if we present something from these joint angles, we can readily implement that. But the problem there will be that mapping this joint angle to the robot workspace as we did in the previous slide. So that is our kinematics problem or forward kinematics problem. And that is often easily solvable, that moving from joint angle to the robot workspace coordinates. But the inverse kinematics problem is sometimes more difficult, that is convert these Euclidean XYZ coordinates to robot's joint angle coordinates. And often it has multiple solution instead of a unique solution. So in this next set of slides, what we will do that in this simple robot, we have only two joints and which we represent by alpha and beta, and we represent the configuration space in 2 dimensions using this alpha and beta. And any motion planning we can, if we can solve in this alpha beta space, that it will give me a series of configuration by which I have to take the joints, and the result will be that the end effector will come to our desired position. So how we can do this, and of course we will not always deal with a single simple these 2 joints of robot. So let us we are talking about all these workspace or configuration space, but first let us look at the definitions. So on the right hand side you can see examples of configuration space, and this this is a triangular robot. We will talk about this triangular robot multiple times. So the configuration space is this space is a transformation from the physical space in which the robot is of finite size into another space where the space is characterized by that we will have 1 dimension for each degrees of freedom of the robot. So if it is a rigid body robot, we will have the 6 DOF, and the configuration space will also consist of 6 dimensions. And as opposed to that, we here in the figure you can see that P and Q are fixed obstacles, and the R is a triangular robot. We took a basic algebraic shape, and figure B shows that how the configuration space is looking like. That you can see this these inclined lines here, which are parallel to this line. You can notice that. So the exact equations we will solve in the next lecture. But in the this lecture, you can just find that how the physical space or obstacle in physical space change their shape in the configuration space. And within this configuration space, there will be 2 types of space. There will be a space where the robot cannot move. Now this space may consist of the physical obstacles. This space can also consist of space where the robot cannot move due to its structure. That means due to the linkage structure. Let's say, for example, if you look our hand, that we have an elbow joint, we have this forearm, and then we cannot move. Like say, for example, I cannot touch with this hand the back of my arm because there is a constraint due to the structure of the hand. And similarly, in configuration space also, even if there is no physical obstacles, there can be some obstacle space due to the structure of the robot. And whatever is not in this obstacle space, that is the free space where the robot can move. And our motion planning job will be to set a set of points within this free space. Through this, the robot can move and complete its task. And when we are so the free path between an initial configuration and a goal configuration is the path which lies completely in free space and does not come into contact with any obstacles. So this will be the end goal of the motion planning algorithms when we are using it in the configuration space. And you will see at the later part of the lecture that we can use the similar set of algorithms that we learned earlier, like A star or value policy iteration for the configuration space. So as opposed to configuration space, the task space is a space which the robot task can be naturally expressed. So this is one example that if the task is to control the position of that tip of a marker on a board, then task space is the Euclidean plane where the marker can move. if the task is to control the position and orientation of a rigid body, which is 6DOF, then it will be the 3-dimensional or the 6-dimensional space consists of all the 6DOF. And the workspace will be the specification of configuration where the robot can reach. So for example, often so far we mostly worked on this workspace, and that's why we express the motion planning in terms of this Cartesian coordinates. And it has the advantage that we can visualize it. It will be maximum 2D or 3D. And we can also understand the algorithms better in the workspace because, again, the reason is we can see what's happening. So this is one example of this configuration space of a simple robot that we already discussed about. And here there are two joint angles, this Q1 and Q2. And each of these joints, they can make one full circle, although due to this, the linkage structure, we understand that it may not make the full 360-degree movement, but its configuration space will be this Cartesian product of these two circles, S and S here, and this torus, and the inner and outer radius of the torus will be determined by this L1 and L2. And the configuration space C is the space of all possible configuration of the robot, so which will be lying on this torus, which itself lying on this say this R cube or the space defined by the real number sets. But even in the very soon you will see that due to this linkage constraint, the robot may not able to reach all possible points on the surface of the torus, and we will have a subset of points within the surface of the torus, which will define the free space. So these are some more examples, again taken from the book of the Russell Norvig. Again, here, at this point, you may not understand that how we are exactly getting this shape. But what you can see here, that this is also a similar robot in the like the previous one. But here also we have this gripper structure. And if you see here, that we have similar structure has been reproduced here. One thing you see that since there are two joints, so we represent it in a two-dimensional place. But there is also, you can see there is an obstacle here, which make it impossible to move the end effector in certain position. And this gripper structure, it's exactly been reproduced here. So again, at this point, you may ask that why we have exactly this shape, and it will also point something that often this configuration representation is also not simple. Say, for example, if I ask you to find an equation of this curve here or this curve here, so if I want to exactly represent this configuration space, I need equation of this graph, right? And that is one problem when we try to do configuration space or do motion planning in configuration space. Of course, there are some solutions of that we will represent in subsequent lectures. But I just want to highlight that when we are working in workspace, I can physically see that if I put a geometric shape here, the obstacle is exactly in that shape. But in configuration space, the shape of the free space or obstacle space is determined both by the shape of the obstacle as well as of the shape and structure of the bot. So this is some more example. And the last one here on the corner, it's also showing this moving position. Again, all these examples are taken from the Russell Norvig book. So so that you follow, I put the figured numbers. And this one is also showing a prospective motion path that moving the bot from one source to destination. Okay. So yeah, I'll just move to the next slide. Yeah. So these are some more examples where we purposefully make some a bit more simplified representation. So here we have this bot, and the obstacle is a very specific geometric shape. And that's why in the Euclidean space, this XYZ space, we are getting this uh, structure like a pillar here. You can also imagine that as if it's a pillar at the corner of the room. And only this, so here you can see that it's pretty easy to understand that the robot can never move onto even the z-axis place also. And the robot's configurations space consists of this XYZ. While here, since we have a moving obstacles, this circle is moving on. That's why we are getting this structure that the robot, when it will be here, the obstacle will be moved here. So there we have free space here. But when it move at this position, we have get this structure here. So this example is showing that how we represent basic geometric shape into configuration space. Again, in a later lecture, we will exactly derive these equations of that, but it will give you some concept that how the configuration space differs from the workspace. So this, the first one is, you can see, is more or less similar to the workspace because it was not moving. But if I say solve this moving obstacle problem in workspace, like our previous example that I told, that if my hand is also moving when I am moving this robot end effector, so what I have to do, that I have to take picture continuously and solve this value iteration problem also multiple times because the hand is moving and the obstacle position is moving. But here in the configuration space, I can, if I know the type of movement of the obstacle, I can define the obstacle space accordingly, and I can plan the movement of the robot within this free space. So even if the obstacle moves, I can still not hit the obstacle. So when we are talking about motion planning, let us be a bit more formalize it, or the instructions. So what we do that we first define the configuration space by defining the space with one dimension per robot motion or pose per DOF. So for a rigid body, we have 6 DOF. So map robot to a point in the space, or the initial position of the robot will be a point in the space where we start. And that is one advantage of configuration space, that I need not to separately solve the problem for the translation and rotation. I can represent all configuration by a single point. And the C space or configuration space consists of all possible configuration of the robot. And the obstacle space is the locus of the infeasible configurations. It's due to either obstacle or the structure of the robot itself. And motion planning is usually done with 3 steps, that we define the configuration space. Well, we can discretize the configuration space, and we'll look at other alternatives to do that also. Then we convert this motion planning problem into a search problem, as we already learned. And each planning problem may have a different definition of C. For example, when we 3DOF for a mobile robot in a static environment will be different from a 2DOF of a mobile robot in a static environment. Okay, so again, it depends on the configuration of the robot. And then, of course, for a 5DOF mobile robot, it will be 5DOF space. So if you decide that I will have a robot and I will only move it in 2 directions, it will be different than if you also consider the robot will go in 3 dimension, or it will become a drone, or you will also require the orientation of the robot. Say, for example, in one class, I show you a video of a warehouse simulation. Now, say your job is to bring the robot from this corner to that corner, and you really do not care about the orientation of the robot. So you want to physically bring the robot there. So then you can configure the configuration space maybe as at a 2 dimension X and Y, same as workspace, or maybe 3 dimensional X, Y, Z, because you do not care about the orientation. But then you imagine that you want to deliver an object there, and there is a fixed space bought at the destination, and it has to orient itself with the orientation of the robot. So then your configuration, your workspace remains same, this XYZ, this floor. But the configuration space then should also consist of the orientations of the robot. Maybe in 2 dimension, it will have only only the yaw movement will be there. So that theta you have to consider in the configuration space formulation. and obstacles in C space that this is the set theoric notation, that for each obstacle, we map the obstacle points from the workspace to the configuration space and take union of all these points. And the obstacle of course, we can also have non-free space due to the robot structure, but we may have multiple obstacles. So for each obstacles, we have to map those points into the configuration space, and we have to take union of them. So we will go through this algorithm. There are this star algorithm, which discusses how we present obstacles or different types of patching of obstacle and the robot. So that we will discuss in the next lecture, where we will go into further detail of this algorithm. So now there are three main approaches of the motion planning. One is the exact algorithm, which we are trying to, I am showing you pictures, or we will try to do in the next class. Exact algorithm will be that we will define the configuration space. We will represent all obstacles and robot linkage structure, etc., in this configuration space, and then we will solve the problem. Second is that the search-based planning, where here the abbreviation SP stands for shortest path and LC stands for label changing algorithm. The label changing algorithm is a generic term where we consider all these search algorithm like A-star, Dijkstra, etc. So the search-based planning we will look at in subsequent slides, where we convert this configuration space by discretizing it into a discrete motion planning problem. And once we do that, although in the slides, we will visualize it in 2D, but even if it is in 6D or higher dimensional space, by discretizing, we can use the same set of algorithm like DFS, BFS, Dijkstra, or value iteration within this discrete space, and that will solve our motion planning problem. Third approach is the sampling-based approach, where we will not explicitly represent this obstacle space, but we will have a function that which will sample the configuration space and return me that whether it is an obstacle or whether it's a free space. And the sampling based planning we will look at next week lecture when we'll discuss about this RRT star algorithms. Okay. So today we will just spend a few more slides on this, solving this motion planning in configuration space by converting into a state space search problem or a shortest path type of problem. Problem will be that there may be some suboptimality. We will discuss about that in subsequent slides in further details. So this is one approach where we did it very simple, that imagine the left-hand side. This is the configuration space. Also, it looks like the workspace, but just imagine that we have only two DOF, maybe alpha and beta of our two DOF robot. And these oval shapes are obstacle space. This is the robot. And here, and what we have done, that we evenly discretize the whole space. So this is very similar demonstration that we did during the value iteration class, that we took the workspace and discretized it into 2020 grid. But here, instead of the workspace, we discretize the configuration space. But even if we discretize the configuration space, the problem remains same, and we can use the similar set of algorithms. Now, there may be some problem, so which is easy to visualize in workspace. So for example, say here, I will just turn on the highlighter here, that there is a small passage here. So in this configuration, when we are discretizing the whole configuration space in evenly sized cell, what happens that here, this cell right here where the laser pointer is, this is something termed as a mixed cell, because this cell consists of both free space and this obstacle space. And if I use the same size of discretization, I will get the whole space as obstacle space, and my motion planning will only happen on the circumference of this. So I cannot get a motion path in between these two obstacles. And this is one problem. So how do I know that this is the gap will be this much? So there is no way I can know that. And if I just increase the cell size, remember that this A-star algorithm or many of our BFS type of algorithm, their complexity is exponential, that is, the space complexity is exponential. So if I keep on reducing the grid size, the algorithm will take too much time or will not run. So how can I know the best size of cells? Okay, that where this I can still make a motion path in between the two gap between the two obstacles. Okay, that in this particular size, we cannot do that. So these are some examples of our very well-known algorithm. So the left-hand side is the same problem. In all this example, you can see that there is no path at the neck of the obstacle. And this is the execution of the BFS algorithm, breadth first search. Right side is the DFS algorithm, and you can see that the DFS takes more time. BFS is quicker. And then we have the Dijkstra's algorithm and the A-star search algorithm. So here we can again revisit the same problem, that when we learn this BFS, DFS, A-star, we told that BFS is also an optimal algorithm. A-star is also optimally efficient algorithm. Then for the same problem, why we have different motion path? Which one of them is optimal? Because optimal can be one only, or if there is multiple optimal, then are all these paths are optimal path? So that is one question. But the bigger problem that we will answer maybe after 2 or 3 slides. But the bigger problem is that can I make a path through this Suez Canal or the Panama Canal, whatever you tell, that where I can make a path between this gap or between the obstacles through this gap. So in terms of optimality, often we have to tell that with respect to which parameter we are trying to optimize it. Say, often in the class, I give you the example of aircraft motion planning, and we can do motion optimize it in terms of the fuel consumption, time it spent, distance traveled, and so on. So in these examples, again, we can define optimality in terms of the number of cells it visit or the total distance it takes. And depend on this optimality criteria, we define the optimal. And as we saw during this passive reinforcement learning example, that often the optimality is defined in terms of the perceived model, not in terms of the true environment. But if we look back, that if we can improve this, of course, the best path will be that if I can make a path in between through the two obstacles, that will be a better path. So how we can do this? So these mixed cells, we have multiple way of solving this problem with mixed cell, where a cell contains both free space and obstacle space. One is progressive cell decomposition, that if a cell is a mixed cell, only the mixed cell I will further divide it into even smaller cells. And so the 8 cells allows we discretized also robot movement at 45 degree, 360 degree by 8. If we now make a 16 cell decomposition, we have to make 22.5 degree of motion. That means we will be able to instruct the robot to orient itself, say, at this much of angle. If we just imagine in terms of the workspace. So can we adapt the cell size or number? Because by brute force, using smaller and smaller cells is not the best solution, because many of our algorithm has space complexity, which is exponential in terms of the branching factor or the depth. So there are two approaches we will discuss. One will be using potential field. That is very similar. You will see that we already looked at a very similar concept. And another is a skeletonization, in which we will change this higher dimensional configuration space into a lower dimension space, where we can efficiently run our state space search algorithms. And also, we already talked about that we have to run these algorithms after representing the obstacles in the configuration space. Okay. So the first idea is potential field. So in the potential field, what we will do, that we will define a function on the free space, and the value grows with the distance to the closest obstacle. So, and here in the picture, you can see that we put this blurry field and around these obstacles, and it is just to ensure that the robot is keeping safe distance from all obstacles. And also there is a trade-off between the clearance and path length, because if we increase the clearance, the path length will also be increased and we may not get the optimal path. So this growing the size of obstacle is very similar that we discussed during the value iteration algorithm. So here also we use the reward structure to represent the hand, which was our obstacle. And when we did not have any uncertainty in movement, we have the same structure. But as we increase the uncertainty in movement, you can see that this hand size is growing up because the negative rewards, they were distributing in neighboring field. And the result is the motion path, it is much smaller here, almost like a straight line, but here it is longer. So in potential field also, we did a similar concept that we grow the size of obstacle to maintain a minimum clearance from the obstacle at a trade-off that the path length may also increase, and it will maybe become suboptimal. Alternative is the skeletonization approach, in which we reduce the dimension of the configuration space at a lower space. One possible way of doing it is we define a set of points which are equidistant from all obstacles, or they are maintaining a separation from obstacles. So in this context, you can remember there is a cobot standard which talks about keeping a separation distance from his human operator. Cobot stands for collaborative robot. So here we define a set of points which are equidistant from all obstacle or nearly equidistant, and we define a graph through these points, and then it becomes that we have to solve a search problem within this set of points which are equidistant from the obstacle. And this word skeletonization is used because we are converting, say, a higher dimensional 6-DOF configuration space into a one-dimensional set of points which are equidistant from all obstacles. But it can also result suboptimality. It can also result a motion path, both approaches, which may require a sharp turn of the robot, because, say, for example, you have a big airplane and then it has been instructed to go to a taxiway which is at a very high angle. So even it reduce the total distance covered, it will take more time because turning a big aircraft will take too much time. So in next lecture, we'll also talk about this holodromic and non-holodromic robots. So it often this motion planning algorithm may require an extra smoothing step to make sure that the output joint angles, those are easily achievable by the robot. So here, this is the formulation of the motion planning problem. And this is very similar to our old problem, the piano movers problem. So the piano movers problem is something related to moving this piano through this set of obstacles. And this is the final desired position, say. So we define a world in which world is we represent it by the set of real numbers. This is the 2-dimension or 3-dimension. We have a semi-algebraic obstacle region O, and we will in the next class we'll find the equation which define the structure of O for a very simple example. Similarly, a semi-algebraic robot which is also defined by W, and why we also, as we saw in the previous pictures, that the configuration or the obstacle space, it also depends on the gripper structure or the linkage structure of the robot itself. Now, this configuration space is determined by all possible points, which is each dimension constitute to one, correspond to one DOF of the robot. A configuration Q, a point in the configuration space will represent the initial configuration of the robot, considering both its position and orientation. And then we will also define another point as the goal configuration. And the motion planning algorithm is setting another set of points which will take this, connect this initial configuration to the goal configuration. And in the previous slides, as we see, that we can discretize the space and use our already known discrete planning algorithms to get this set of points. Now, also there is alternate way, as we discussed, like the sampling based approaches, which we did not discuss now. But the problem is that this is a PS space complex problem, or PS space hard. So what is P space hard? So in this context, we will just briefly tell about this complexity analysis, and we did not to go into detail. So there is a set of problems which is solvable in polynomial time. And as we discussed during the DFS BFS lecture, polynomial time means that the total time or space requirement of the problem is polynomially dependent on the input size, which consists of our P class. Then there are NP set, where we have a set of problems which is verifiable within a polynomial time. What do we mean by verifiable? That they are also verifiable, that they are whether they are solvable or not solvable within this polynomial time. And there is this set of NP complete problem which can be solved, but they are not can be solved within a polynomial time. And most of our state space search problem which belongs to the NP complete class. And the NP complete class is also within the NP hard class. So many times you will see the roboticists tell that a star is NP hard problem, which is both true, but more precisely that those are NP complete problem because these are decidable. While there are problems like the halting problem, which tells that whether a program will halt or stop for any given set of input, and that set of problem is not decidable. And those are class of problem which are NP hard but not NP complete. So here we mostly talk about NP complete problem. So how we solve this NP complete problem? So there are all set of courses works on approximation algorithms, which basically relax the optimality criteria, that we try not to get optimal path. We try to get something which is reduce the overall cost function. And this overall cost function may be in terms of the cells visited, as we are discretizing the cells, the Cartesian workspace that we are getting shortest path, like in the Dijkstra's set of algorithm, or set of physical parameters that I am reducing the number of steep turns or angular movement or the total power, fuel consumption, etc. And always these algorithms, we discuss about this trade-off between completeness, efficiency, and minimum distance, that we relax one criteria to satisfy another criteria. So yeah, we already discussed these cobot standards, that where we are not only interested on the shortest path, but we are also interested to keep a minimum separation distance from the human operator. And as we saw in the skeletonization or the potential field, we try to do the same, keeping a minimum separation distance from the obstacles by trading off the path length or the optimality in terms of the total distance traveled maybe. So finally, in this lecture, we just learned the basic concept of the configuration space and that various definitions of configuration space, workspace, task space, etc. We formulate the problem of motion planning in C space, and we see that by discretizing, we can keep on using our same known algorithms to solve the motion planning problem. We discussed about the mixed cell problem, where a cell consists of both free and obstacle space, and we can do progressive cell division. And then we talk about this potential field and skeletonization, where we have ways by which we ensure a minimum separation distance from obstacles. And we briefly discuss about this trade-off among this term efficiency, completeness, and optimality. So in the next lecture, we will take a very simple example, and we will see that how we can find a set of equations which decides the obstacle space, and we can do an exact solution of the motion planning problem. While in subsequent lecture, we will discuss about this RRT star, the sampling based motion planning approaches. Okay. So with that, I will stop sharing and I will just stop recording.